we're going to look at how we balance redox reactions. So trial and error techniques that are used for balancing other reactions end up being very difficult and time consuming when we're balancing redox reactions, so we're going to take a more systematic approach. So we're going to start by separating the reaction into two half reactions. So every redox reaction will involve an oxidation, which is where a species is losing electrons, and then a reduction half reaction where a species is gaining electrons. So once we have the reaction separated into these two half reactions, we're going to balance each of the half reactions. So first we'll balance the atoms just as we do with any other chemical equation, and then we need to balance the charge, and we'll do this by adding electrons to either reactants or products. Once we've balanced each of the reactions, we now need to adjust the number of electrons in each reaction so that the electrons lost in the oxidation is equal to the electrons gained in the reduction. The reason for this is that the electrons that are lost in the oxidation have to be used in the reduction, so the number of electrons in each step has to be equal. So we'll do this by multiplying each equation by some coefficient. Once we have the number of electrons in each reaction equal to each other, we're going to add the two half reactions together to give the overall balanced equation. And because there are the same number of electrons being transferred in each step, the electrons will cancel. So let's look at an actual example. So in this reaction, aluminum is being oxidized by copper 2+ to form copper and aluminum 3+. So the very first thing we want to do is divide the equation into half reactions. So the reduction half reaction in this reaction is going to be copper 2+ being reduced to copper. And so since copper is being reduced, copper is reacting as the oxidizing agent. In the oxidation half reaction, aluminum is going to be oxidized to aluminum 3+. And so since aluminum is being oxidized in this reaction, it's acting as the reducing agent by providing the electrons that will then reduce the copper 2+. So now that we have the reaction divided into half reactions, we're next going to balance the atoms. So in this case, because we just have metal ions and atoms, all of the atoms are actually balanced, so we can go on to the next step. So next we want to balance the net charge by adding electrons. So we want to look at each of the two equations and see what the charge is in the reactants and the products. So in the reduction reaction, we're starting with copper 2+ in the reactants and neutral copper in the products. So in order to balance the charge, we would need to add 2 electrons to the reactant side so that we have neutral charge on both sides of the reaction. In the oxidation half reaction, we have neutral aluminum in reactants and aluminum 3+ in the products. So in order to balance the charges here, we'd need to add 3 electrons to the products. So now we want to make the number of electrons gained in the reduction half reaction equal to the number of electrons lost in the oxidation half reaction. So we're going to do this by multiplying each of the equations by some coefficient. So in this case, if we multiply the reduction half reaction by 3, that will give us 6 electrons total being transferred. And if we multiply the oxidation half reaction by 2, that will also give us 6 electrons transferred. So now we have the number of electrons balanced in each of the two equations, and so we now want to add the two half reactions and cancel any species that are on both sides. So in this case, the only species that are present on both sides are the 6 electrons. So the electrons will cancel, giving us this overall balanced chemical equation. So this example was relatively simple because it only involved aluminum and copper ions and atoms. Now reactions can get more complicated, and we also need to use certain techniques depending on the conditions that we're using. So now let's look at an example of balancing a reaction where we're in an acidic solution. So this means that we have water and hydronium, which will represent just as H+, available for balancing the reaction. So the first thing we want to do is divide the reaction into half reactions. Now in this case, it might not be quite as obvious what the reduction and oxidation half reaction should be as it was in the previous example. And so what we first want to do is assign oxidation numbers for each of the atoms in the ions and compounds that are involved so that we can determine what's being oxidized and what's being reduced. So let's first look at N2O. So N2O is a neutral molecule, so this means that the nitrogen oxidation number plus the oxygen oxidation number has to be equal to 0. So if you look back to chapter 3, where redox reactions were first introduced, you might want to review the rules for assigning oxidation numbers. So the rule for oxygen is that it usually has a 2- charge unless it's bonded to fluorine, which is more electronegative than it, or if it's in a peroxide or superoxide. So neither of those is the case here, so we'll assume that the oxidation number of oxygen is -2. So now we just have to solve for the nitrogen oxidation number, which will turn out to be +1. So we're starting out with nitrogen in the +1 oxidation state and oxygen in the 2- oxidation state. So now let's do the same thing for NO. Once again, this is a neutral molecule, and so the sum of the oxidation numbers of all the atoms has to be equal to 0. We'll next assume, once again, that the oxygen is in the 2- oxidation state, and so now we just have to solve for the nitrogen oxidation state, which would end up being +2. So on going from N2O to NO, the nitrogen oxidation number is increasing from 1 to 2, and the oxygen oxidation number is staying the same. So this must be the oxidation reaction, and so we can write our oxidation half reaction as N2O being converted to NO. So we can assume that the other half reaction involves chromate and chromium 3+, and that it's a reduction, but let's confirm this by determining the oxidation numbers of all of the atoms in the relevant species. So if we start by looking at chromate, the chromate oxidation number plus the oxidation number of all of the oxygen atoms has to be equal to -2, because chromate has a 2- charge. So we'll once again assume that the oxygen oxidation number is -2, and so now we can just solve for the chromium oxidation number, and we find that it's 6+. And then for chromium 3+, we know, because this is just an ion of a metal, we know that the chromium oxidation number has to be 3+. So in this case, the chromium atom is being reduced from 6+ to 3+, so our reduction half reaction involves reduction of chromate to form chromium 3+. So now that we know our oxidation and reduction half reactions, we next want to balance the atoms. So we're going to start by just balancing atoms that are other than hydrogen and oxygen. We're going to balance the hydrogen and oxygen later. So in the oxidation half reaction, we see that the only non-hydrogen or oxygen atom is nitrogen, and we have 2 nitrogens in the reactants and 1 in the products, so we would need to add a coefficient of 2 in front of the NO. For the reduction half reaction, we have 1 chromium atom on each side of the equation, and then just oxygen, so that's balanced in terms of chromium. So now we want to balance oxygen atoms, and we're going to do this by adding H2O as our source of oxygen. So in the oxidation half reaction, we're starting with 1 oxygen in the reactants and 2 in the products. And so to balance this, we would add a water molecule to the reactants. In the reduction half reaction, we have 4 oxygens in the reactants and none in the products. And so we would balance this by adding 4 water molecules. So now we've balanced the oxygen, but we've introduced hydrogen into the equation. And so because we're under acidic conditions, we know that there will be a large amount of protons present, and so we can balance the hydrogen atoms by adding protons to the equation. So in the oxidation half reaction, we would need to add 2 protons to the products so that we have the hydrogens balanced. And in the reduction half reaction, we would add 8 protons to the reactants, again to balance just the hydrogen atoms. So now we're in a situation where the equations are balanced by mass, so all of the atoms are balanced, but the charge on each of in the reactants and products are not currently equal. So we're going to now balance the charge so that we're going to balance the net charge by adding electrons. So let's start by looking at the oxidation half reaction. We want to determine what the charge is on each side of the reaction, and then decide how many electrons we need to add in order to balance out that charge. So in the reactants, we just have 2 neutral molecules, so the charge is 0 overall. In the products, we have a neutral molecule and 2 protons, so the charge is 2+ overall. So in order to balance that charge, we would add 2 electrons to the products so that we have neutral charges on both sides of the equation. Now in the reduction half reaction, in the reactants we have 8 protons, but then we have 1 chromate ion, so the overall charge is 6+. in the products, we have a chromium 3+ ion in a neutral molecule, so the charge overall is 3+. So now we want to balance it so that the charge on both sides of the equation is 3+, and so we would do this by adding 3 electrons to the reactants. So now we have our two balanced half reactions, and so we ultimately want to add them together to give our overall balanced reaction, but first we need to have the number of electrons gained in the oxidation reaction, in the reduction reaction, be equal to the number of electrons lost in the oxidation reaction. And so we can do this by multiplying the reduction half reaction by 2, and the oxidation half reaction by 3, so we have a total of 6 electrons transferred in each step. So now we have two equations where we have equal number of electrons transferred in each, and so now we want to add the two together to give the overall balanced equation. And when we do this, we want to cancel any species that are present on both sides of the reaction. So we know that there are 6 electrons transferred on each side of the reaction, so the electrons will cancel. We then can see that there are protons on each side of the reaction, so the 6 protons in the products will cancel, and 6 of the protons in the reactants will cancel, so we'll end up with 10 protons in the reactants. And then we also have water on both sides of the equation, so 3 of the water molecules in the reactants will cancel, and 3 in the products, leaving us with 5 overall. So now if we actually add the two equations together, this gives us the overall balanced equation. And in some cases, we'll need to reduce the coefficients to the smallest whole number, but in this case, they're already reduced, so this is the final balanced chemical equation.